Welcome to this summary video on Diploma Program Physics. This is going to cover topic 2.2 under mechanics, which is forces. And the first thing you have to, these are the understandings from the Diploma Program Guide, and let's start going through them. So let's just, before maybe we start going through the understandings, what do we mean by a force in terms of the Newtonian sense? Well, the force is either a push or a pull, you can say, and it's measured in, most commonly the symbol for a force is a capital F, and it's measured in, the unit for force is the Newton, which is the same as kilogram meters per second squared. It's the derived SI unit. So firstly, they want you to understand that when we work with forces, we treat objects as point particles, and this is linked to the concept of the free body diagram. So I might have a block of wood of mass m resting on a table. Basically, when we draw the free body diagram, we consider all the forces acting from one point. And that point is the center of mass of the particle. So in terms of the block resting on a surface, we draw a point, we'd have one force acting vertically downwards, mg, that's the force due to gravity, and we'd have another force acting upwards, that would be the normal reaction force. In terms of, let's do another example, let's say we had a car, it's acted on by, let's say, four forces. We have a force of gravity, downwards we have a contact force, upwards we have a thrust force to the right, and we have a frictional force to the left. Gravity, contact force. But we could draw a free body diagram for the car. Would be a point acting from the center of mass of the car. This would be the forward accelerating force. This would be the frictional force. This would be mg downwards, and this would be contact force upwards. So free body diagrams act from the center of the mass, and all forces go out from the same point. Now, what do we mean by translational equilibrium? Basically, it means that if we were to draw the free body diagram, for example here, and all the forces were to cancel out in all directions, then the sum of the forces would equal 0, because remember, forces are vector quantities, so this force n upwards, if that cancels with the force of mg downwards, we have translational equilibrium in the y direction. So basically, it's the cancelling out of forces. And if we have translational equilibrium, this links to one of Newton's laws of motion. We have Newton 1, Newton 2, and Newton 3. This links to Newton's first law of motion, that if we have translational equilibrium, if there's no resultant force acting on the body, then either it will stay at rest, or it will continue with constant velocity. In the same direction. However, Newton's second law of motion says that if there is a resultant force, then the object will accelerate. And the formula for working out the resultant force is F equals ma. What Newton's third law of motion says, is that all forces come in pairs which are equal and opposite. And they don't always have to be in contact. So for example, there's a force, let's say this is the sun, and this is the earth. Then there's a force of the sun on the earth, FSE, let's call it, but there's also a force of the earth on the sun, FES, and they are equal and opposite, and in this case they act at a distance. So the only thing we haven't talked about is solid friction. Basically, due to the roughness between two surfaces, there is a force. If I have an object there's a force acting to oppose the motion, which is acting in the opposite direction to the motion, if you like. So we can have three scenarios. We can have, in most cases, or in a lot of cases, we actually regard or disregard friction, but when friction might be needed to take into account is when we have, for example, a wooden block on a surface. So there might be a friction between the wooden block and the surface. This could be wood, and this could be also I guess a wooden surface. If we pull the wooden block a little bit and it doesn't move, then there'll be an equal and opposite force to the left, little f, opposing the motion. However, I might increase the force. Just move this block a bit more into the center. Okay, we haven't actually moved the block, I'm just moving it to fit it on the page. I might increase the force to the right just until the point before it moves. So now big F has increased, but also the frictional force, little f, has increased just to the point before it moves. And then anything above that point, so if then I increase the force a little bit more, what happens is there is a frictional force. Now we're in motion, so now it would have a velocity v. As soon as it's in motion, we have a dynamic coefficient of friction acting in the opposite direction, but it's actually slightly less than the maximum static friction, which is the friction it has when it's stationary. So you can represent this using a graph. So if this is the frictional force and this is the pulling force, the frictional force increases until we get over a threshold value, the maximum static friction, and then it drops down and we have a constant dynamic friction. This value here would be Fd for dynamic friction. This value here would be Fs max, or the static maximum value of static friction. And there are formulae for these. And they depend on the reaction force. So the maximum value of static friction, Fs, is given by mu, which is the coefficient of static friction, times by r, which is the reaction force, the force which is normal to the surface and the object. And the value for the dynamic friction is the dynamic coefficient of friction, mu d, times by, again, the reaction or normal force.